Hi, I'm Arijit Biswas, lead architect for Sapphire Rapids. Sapphire Rapids is our next generation Xeon Scalable Processor to be in production in the first quarter of 2022, with ramp beginning in the second quarter of 2022. We designed Sapphire Rapids to establish a new standard in data center architecture. It's architected to deliver great out-of-the-box performance with enhanced capabilities for the breadth of workloads and deployment models in the data center. Sapphire Rapids delivers a step function in performance across a broad set of scalar and parallel workloads. More importantly, it is fundamentally architected for breakthrough performance in elastic computing models such as containerized microservices, as well as the rapidly expanding use of AI in all forms of data-centric compute. Sapphire Rapids introduces several new capabilities that provide latency-optimized solutions throughout the microservices service mesh, and we will cover some of those key capabilities in this session. Our overall architecture philosophy for Xeon is to deliver the best infrastructure for the data center. A big part of that is to design for the present state and future of cloud computing. The cloud spans a wide range of usages. More and more, we see clear trends toward disaggregation, building out microservices in the form of a service mesh, and a need to deliver data center scale elastic compute, all under tight service level agreements. Challenges in cloud computing include such things as appropriately sizing memory, demand for cloud-based services such as training from OpenAI machine learning, which is doubling every 4 months or so, and seeing that socket-level performance using traditional compute paradigms has plateaued. These are leading to a realization that simply throwing more hardware at the problem is insufficient. There's a clear need for the software and hardware developers to work together to optimize systems. An example of this would be using accelerators to improve performance at scale. We'll need a system-level approach that's a co-design of software, hardware, and accelerators, all moving toward a more tightly coupled distributed systems. Our new Xeon architecture is optimized to deliver great performance, big improvements, and new capabilities across all of these areas. I want to take this opportunity to deep dive into microservices, what they are, why they're important for the Xeon platform, and why Sapphire Rapids on EagleStream is the best platform for them. Microservices is an architectural style that structures an application as a collection of services that are highly maintainable and testable, loosely coupled, independently deployable, organized around business capabilities, and owned by a small team. The microservice architecture enables rapid, frequent, and reliable delivery of large, complex applications. IDC is projecting an 11x growth in container instances between 2018 and 2023. Additionally, cloud microservices cycles are growing to greater than 50% of all CPU cycles in the cloud. Also, multi-cloud management is proving critical for edge services. We're making numerous improvements on Sapphire Rapids specifically to better serve microservices by delivering higher throughputs at lower latencies and low jitter, as well as significant overhead reductions through acceleration. For example, we're optimizing service mesh software with features such as DSA, QAT, AIA, and AVX, and I'll go into a little more detail on some of those later in this session. Core instruction set architecture optimizations, including crypto acceleration, accelerates container runtime performance. The new advanced matrix extensions instruction sets delivers total cost of ownership savings for AI inference. And also optimizing at a platform level with technologies such as the Intel Ethernet 800 network adapters with features like application device queues can drive up to a 10x reduction in tail latency for in-memory caches. At the end of this presentation, we'll point you to a demonstration showing more on this capability. At the heart of Sapphire Rapids is a new modular tiled architecture that allows us to scale the Xeon architecture beyond physical reticle limitations. Sapphire Rapids is the first Xeon product built using our latest EMIB silicon bridge technology at a 55 micron bump pitch. This innovative new technology enables independent tiles to be integrated in a single package, realizing a single logical processor. The resulting performance, power, density, and software paradigm is comparable to equivalent monolithic silicon. We're now able to increase core counts, caches, memory, and I/O free from the physical constraints that would otherwise have been imposed on the architecture, leading to difficult compromises. This base SoC architecture is critical for providing balanced scaling and consistent performance across all workloads. This is key for data center scale elasticity and achieving optimal data center utilization. With this architecture, we're now able to provide software with a single balanced unified memory access, where every thread has full access to all resources on all tiles, including cache, memory, and I/O. The result is consistent, low latency, and high cross-sectional bandwidth, achieving over a terabyte per second of aggregate bandwidth across the entire system. This is one of the critical ways we achieve low jitter on Sapphire Rapids. While Sapphire Rapids delivers out-of-the-box scalability for existing software and ecosystems, users can enable clustering at sub-NUMA levels, as we have supported on prior generation products, as well as new sub-UMA levels for additional performance and latency improvements. These on-die clustering options are critical to manage latencies, as the ever-increasing counts of cores, accelerators, and I/O results in larger and larger meshes across the system on chip. In the case of Sapphire Rapids, our tiled architecture creates natural clustering opportunities that our clustering solutions, both old and new, take advantage of. The standard single UMA, or Uniform Memory Access, domain mode for all previous Xeon CPUs is all-to-all mode, where there is no clustering. This has been our default out-of-the-box mode up until Sapphire Rapids. There are no latency optimizations in this mode. All cores have full access to all channels of memory bandwidth, with one contiguous memory address range being interleaved across all 8 channels. In this mode, there is no affinitization between cores, caching and home agents, which we call CHAs, or memory controllers. However, no software changes or optimizations, nor specialized operating system or memory management support is needed for this mode. As a result, any core making a demand request for memory can be steered via hash to any CHA on any tile in the SoC, and in turn, that CHA can send the request to any memory controller, again on any tile, based on where the requested data is stored. This could result in higher than desired average latencies and latency variability. In order to manage this latency, even on prior generation CPUs, we recognized the need for and introduced sub-NUMA, or non-uniform memory access, clustering modes. Very simply, these SNC modes virtually subdivide the SoC into multiple symmetric clusters. Each is an independent NUMA node to software. Also, the address range is divided equally between the SNC clusters and interleaved only across the channels within a given cluster. Hence, the available memory bandwidth is divided between the clusters. This is still a single caching domain, however, as each cluster can still access the full last level cache across all the clusters, but accesses to a different cluster can result in higher latencies. In order to minimize such accesses, OS support as well as NUMA optimizations to the target workloads are required to make this mode effective. Workloads that cannot be NUMA optimized or that require greater memory bandwidth or capacity than can be provided within a single cluster would not do well in this mode. But for those workloads that do fit within these guidelines, SNC delivers the best latencies and performance for core-to-memory accesses, since it ensures that traffic is affinitized from the core making the request through the CHA all the way to the memory controller. This delivers optimal latencies by ensuring that accesses always stay local to a cluster. On Sapphire Rapids, we support 2 such SNC modes. SNC2, where the SoC is divided into 2 symmetric hemispheres, with half the total cores and 4 memory channels out of a total of 8 each. And on SNC4, where the SoC is divided into 4 symmetric quadrants. A quarter of the total cores and 2 out of the 8 memory channels are in each cluster. On Sapphire Rapids, these cluster boundaries follow the physical tile boundaries, as that provides the best local clustering latencies. While SNC modes deliver the best core-to-cache and core-to-memory latencies, they have some drawbacks that limit their usefulness. The need to NUMA optimize all the software, the reduction in memory and I/O bandwidth, all result in this remaining an opt-in option for users who can meet those requirements. Otherwise, on prior generation Xeons, the only other option was all-to-all mode, which provides no latency optimization at all. On Sapphire Rapids, we introduced the concept of UMA clustering. In this new mode, the SoC is again virtually divided into multiple symmetric clusters, but unlike the SNC modes, software still sees a single NUMA node. As such, the full system address range is interleaved across all memory channels, providing the full socket's worth of memory bandwidth and capacity to all applications. In this mode, the affinity is only between the CHA and the memory controller. As a result, a demand request from a core can be routed to any CHA on any tile and is not guaranteed to go to a local CHA like in SNC modes. However, once there, if the request needs to access memory, the system will guarantee that the request will go to a memory controller that is in the same local cluster as the CHA. This effectively reduces the latency of the overall transaction. While it doesn't deliver the full latency benefit of SNC mode, it does deliver about 75% of the latency benefit on average without the need for any software optimizations or special OS support, and without reducing memory bandwidth or capacity or I/O bandwidth available to an application. This new mode finally provides an excellent option for customers who cannot NUMA optimize their workloads or who require the highest memory and I/O bandwidths while still providing a software transparent way to manage latencies. On Sapphire Rapids, we're supporting 2 UMA clustering modes: Hemisphere, which divides the SoC into 2 symmetric halves, similar to SNC2, and Quadrant, which divides the SoC into 4 symmetric clusters, similar to SNC4. These UMA clustering modes will be the out-of-box default modes on Sapphire Rapids, since no software changes are required to benefit from them. For both the SNC and UMA clustering modes, system memory must be populated symmetrically between the clusters to engage these modes and gain the benefits of the reduced latencies. As stated previously, Sapphire Rapids is architected for foundational improvements in microservices and AI workloads. We're at a data center inflection point. The majority of new apps are deployed as microservices. Microservices are heavily and increasingly used in hyperscale service deployments where best microservices throughput and low latency with strict service level agreements are key levers for compute performance. Amazon, for instance, is predicting that up to 90% of applications will run as microservices within the next 5 years. Because of their disaggregated and distributed nature, microservices deployment drive additional requirements on infrastructure, such as increased infrastructure management overhead, a better service mesh for networking, and the ability to run reliably across multiple cores and servers. The usage of AI is also becoming more and more ubiquitous across the entire computing stack. In order to deliver data center scale elasticity, great AI performance is required across all tiers of compute. These new usages drive 3 new platform needs. 1. CPU microservices and AI acceleration. 2. Infrastructure offload. And 3. Overhead reduction for deployment and memory management. A critical aspect of optimizing for CPU microservices is that it goes hand in hand with enabling better infrastructure offload and overhead reductions. On Sapphire Rapids, we explored breakthrough improvements for the high levels of common mode tasks causing overhead that we see in data center scale deployment models. Instead of traditional approaches, we embarked on a new direction using optimized acceleration engines. The use of acceleration engines is a key trend we've been observing in data centers for a while. We've found these engines to vastly improve processing of these overhead tasks and enable greater utilization of the general-purpose performance cores for higher user workload performance, all for a significantly reduced power and area cost. But we realized that simply bolting on accelerators was insufficient for truly integrating these functions. The challenge of using dedicated acceleration engines lies in the difficulties around software models, usability, shareability, memory management, and so forth. We decided that the best way to truly address these key challenges was by creating a full set of novel technologies to support seamless integration of dedicated acceleration engines with general-purpose performance cores. Technologies such as the accelerator interfacing architecture, instructions, and advanced virtualization capabilities enable us to avoid kernel mode overheads and complex memory management typically associated with such schemes. These provide the necessary base functions to simplify enumeration, software development, and deployment for acceleration engines. Sapphire Rapids supports several critical acceleration engines for processing the most common overheads. A couple that are specifically targeting microservices are the Data Streaming Accelerator, or DSA, and the Quick Assist Technology Accelerator, or QAT. Let's take a closer look at those two. Data center usage models, including microservices, involve significant data movement overhead as part of workload processing. Examples include packet processing, data reductions, and fast checkpointing for virtual machine migration. Sapphire Rapids introduces the Data Streaming Accelerator engine to offload the most common data movement tasks. DSA can move data between CPU caches and DDR memory, as well as I/O-attached devices. In this graph, we show an open virtual switch use case in which, with up to 4 instances of DSA, we see nearly a 40% reduction in CPU utilization and a 2.5x improvement in data movement performance. This results in nearly doubling the effective core performance for this workload. This is just one example that clearly shows the value of offload, both for the work being offloaded to a dedicated engine, as well as the general purpose cycles becoming available for use, increasing the overall effectiveness of compute resources on the CPU. DSA, like all the integrated acceleration engines on Sapphire Rapids, fully supports shared virtual memory, scalable I/O virtualization, and the AIA instruction set, enabling offload and management from user mode, avoiding kernel mode overheads, and greatly reducing memory management overheads as well. Here we see several of the key operations that DSA accelerates on Sapphire Rapids. These include move operations like memory move, copy with CRC generation, copy to 2 destinations simultaneously for replication usages, and data integrity field checks. DSA also supports a group of compare operations, including checks for identical data, creation of delta records, merging of delta records, and comparisons against a pattern. DSA also supports a memory fill operation that can be used to fill a memory range with a fixed value, such as for zeroing out memory, and a cache flush operation to better manage cache data for a given address range. Another acceleration engine is Intel Quick Assist technology. Intel Quick Assist is not new to Intel products. Sapphire Rapids provides seamless integration of the next generation QAT engine, greatly increasing its performance and usability. It's of increasing importance that all data in the data center is secured while processed, transmitted, or stored. Furthermore, the ever-expanding data footprint is progressively maintained in a compressed format for cost and efficiency. Our next-gen QAT acceleration engine supports the most popular ciphers, hash, public key, and compression and decompression algorithms, and can chain these together for single-pass operations. Performing these functions using QAT is significantly faster than the software implementations on the general-purpose performance core and greatly reduces the number of cores needed for these widely supported services. Sapphire Rapids QAT can achieve up to 400 gigabits per second of cryptographic ciphers and verified compression and decompression at up to 160 gigabits per second each. In this example, with the zlib L9 compression implementation, we see a 50x drop in CPU utilization while also speeding up the compression by 22x. Without QAT, this level of performance would require more than 1,000 performance cores to achieve. Improving multi-tenant usages as well as reducing memory management overheads have both been mentioned previously as key capabilities advanced for Sapphire Rapids. Two of the virtualization technologies that enable these are shared virtual memory and scalable I/O virtualization. SVM is the key technology that enables cores, integrated accelerators, and discrete I/O devices to significantly reduce memory management overheads by providing a consistent, coherent view of memory on which all computation can occur regardless of the computation engine. Scalable IOV greatly improves and simplifies scalability, sharing and enumeration of device accelerators, integrated or discrete, versus our prior generation single root IOV technology. Beyond acceleration engines and seamless integration for overhead offload, we also made several architectural enhancements across the product spanning cores, accelerators, and SoC. For example, the AIA capabilities that I've mentioned that reduce microservice startup time, advanced telemetry improvements for optimal microservices load balancing and orchestration, and a number of capabilities such as QAT, DSA, and others to reduce the networking stack overhead with a microservices service mesh. We've been using multiple proxy workloads to develop these capabilities and optimizing the open source software stack to benefit from them. This chart shows the speed up we're seeing in our architectural models and some early measurements on Death Star Bench and other example proxies, normalized at the per core level. This is leading to a substantial jump in microservices workload performance of about 69%, moving from the second generation Xeon Scalable, codenamed Cascade Lake, to Sapphire Rapids, as measured on Death Star Bench proxy workloads. In order to deliver data center scale elasticity, great AI performance is required across all tiers of compute. As we stated previously, this is another one of the major focus areas for Sapphire Rapids. To deliver on AI performance, we introduced AMX, or Advanced Matrix Extension capabilities, using a combination of tiled register files and tiled matrix operation units. These provide massive speedup to the tensor processing at the heart of deep learning algorithms. We can perform 2K integer 8 and 1K bfloat 16 operations per cycle. This represents a tremendous increase in computing capabilities that are seamlessly accessible through industry standard frameworks and runtimes. We augment this with strong general purpose capabilities, large caches, high memory bandwidth and capacity to deliver breakthrough performance improvements for CPU-based training and inference. There are two components in the AMX architecture today. The first component is tiles, which is a new state component consisting of 8 two-dimensional registers, each 1 kilobyte in size. The programmable part of this component simply consists of configure, load, store, and clear. The more interesting operations are carried out by coprocessors that operate on tiles. Tile state is operating system managed, which required new extensions to the Xsave architecture. The second component for AMX is Tml, which stands for Tile Matrix Multiplication, and is the first coprocessor attached to tiles. It's a systolic array supporting all flavors of integer 8 with 32-bit accumulation and bfloat 16 with single precision accumulation. In order to provide a broader view of the underlying architecture behind AMX, we show this diagram. The architecture here is highly flexible and can be expanded to implement further coprocessors down the line to address different types of computation needs. In the current implementation on Sapphire Rapids, we have the Tml Engine as the tightly coupled coprocessor within the performance core. Effectively, it just looks like another functional unit, like another ALU or vector unit, that provides a set of native new instructions available to every core on Sapphire Rapids. The core is still doing all the loop and address management as well as the SIMD processing of the data. The Tml Engine performs matrix multiplications in parallel with the other host activities. The resulting power and performance is much better than simply running these algorithms on the SIMD hardware. The matrix engine is much more efficient, and the remaining work on the host is generally light, so all of the core power budget can be given to the matrix engine and the cache subsystem to feed it. With heavy AMX use, the core is expected to require running at a lower frequency or license level than standard scalar operations, but this should be similar to the frequencies seen when heavily using AVX 512 instructions. The typical flow for a layer in a deep learning topology is for the data to come in straight to the tiles. Meanwhile, the host core is running ahead, dispatching tile loads, while Tml is operating on the ready data. At the end of the multiplication, the tiles are stored to the nearest cache level to the host core, thanks to the tight coupling with the core. Then SIMD code is used to post-process the output and store it to the right location for the next layer to compute and consume. There are software techniques to fuse and interleave these operations so that both the host core and the AMX unit are kept busy simultaneously, which provides maximum throughput and performance. With all these new hardware capabilities, we realized that the most critical aspect is how we're enabling the software ecosystem to develop for and deploy these new capabilities rapidly and with consistently high quality. One API developer tools address the historic problem of developers needing to rewrite their code to take advantage of a new architecture and the new capabilities that it brings. Based on standards, it allows developers and their organizations to pick the best architecture for their business and technical needs without being locked in by proprietary language code. One API enables high-performance development across CPUs, GPUs, FPGAs, and future accelerators with a rich set of languages, performance libraries, and analysis tools. The One API tools also include highly optimized versions of popular open-source frameworks and middleware such as TensorFlow and PyTorch, deep learning frameworks tuned for performance on Intel hardware, incorporating support for new hardware capabilities on Sapphire Rapids like the AMX that we just covered. I'd also like to call your attention to some more specifics on support for Sapphire Rapids in One API. The vTune Profiler memory access analysis for Sapphire Rapids helps to identify memory-related performance bottlenecks. It identifies memory stalls with breakdown by hierarchy available at function and source or assembly level. You can also observe DRAM, persistent memory, and high bandwidth memory to understand NUMA latency and scalability. The vTune Profiler I/O analysis for Sapphire Rapids gives the uncore and device-centric view to locate performance bottlenecks in I/O-intensive applications. It supports any external PCIe device, such as NICs, NVMe storage, FPGAs, GPUs, and so on, or integrated accelerator devices, such as DSA or QAT, to analyze I/O traffic processing details, including Intel Data Direct I/O utilization efficiency. These are just a few of the capabilities. You can check out the One API tools on the free Intel Dev Cloud today, and it's fully production ready. In summary, Sapphire Rapids delivers a massive leap in performance and capabilities to establish a new standard in data center architecture. At the root of Sapphire Rapids is a modular tiled SoC architecture, thanks to EMIB technology, that enables significant scalability yet maintains a monolithic view. It delivers great improvements for monolithic workload deployment models while exclusively optimizing for elastic compute models like microservices, which is what cloud-native applications are being built as. It delivers substantial performance across scalar usages and massive improvements in emerging parallel workloads like AI. By delivering great AI performance in the general compute tier, we enable ubiquitous and pervasive use of AI from the cloud all the way to the edge. With an advanced new core architecture, new dedicated compute engines for targeted work offload and balancing, with industry-leading memory and I/O technologies to feed the massive compute capabilities, Sapphire Rapids is our best platform and a massive leap in capabilities and performance for data center and cloud usages, especially targeting microservices and AI. In this session, we touched on a few key areas of improvement that Sapphire Rapids delivers, like UMA modes for optimal latencies out of the box, completely transparent to software, and how technologies like DSA, QAT, and AMX help facilitate big leaps in microservice and AI performance. This is only a small handful of the myriad capabilities that Sapphire Rapids is bringing to the table, with many more goodies being revealed between now and launch. In the meantime, if interested to see more on Sapphire Rapids, please don't miss these other sessions at Intel On. We're very excited about Sapphire Rapids and can't wait to get it into your hands. Thank you very much.